Hello,
Hi.
everyone. Good
Hi.
morning.
How are you?
I'm very well, thank you. So this is day 4 of the Cyber Science Conference, and the title of today's talk is Energy Efficiency in Low Power and Lossy Network by Abdu. So I'm gonna hand over to Abubakar Halilu to present his work. Thank you.
Thank you very much, Cyril. Hi, everyone. My name is Abubakar Halilu. I'm a postgraduate student here at the University of Salford, Manchester. And for the next few minutes or thereabout, I will be giving a presentation on energy efficiency in low power and lossy networks. It's a privilege for me to share with you all the works that we're doing here at the University of Salford. Low power and lossy networks is nothing but wireless sensor networks, mostly Internet of Things and mobile ad hoc networks. But for the purpose of this presentation is only on Internet of Things. Energy efficiency in low power and lossy networks has been an area that a lot of researchers try to improve over the years. And by way of introduction, Internet of Things is a system of computing devices which contains digital machines, objects, actuators, sensors, and several other devices having unique identifiers in order to exchange and communicate over the network without requiring any human-to-human or human-to-computer interaction. And Internet of Things has been an emerging area of research over the years, particularly in industry and academia. This is a technology roadmap of Internet of Things over the past 2 decades. We've seen its evolution from simple RFID tags to ability to monitor and control distant objects, that is from simple supply chain helpers to physical world web. The motivation of this research is actually a study conducted here in the UK by Cambridge consultants in 2017. They said that at the end of 2016, there were 13.3 million IoT devices connected in the UK alone. And that number is set to increase by a compound annual growth rate of 36% over the next 7 years, bringing the total number of devices to 155.7 million IoT devices. Now, this is in the UK alone. And these areas of this improvement include automotive, transportation, consumer electronics, fast-moving consumer goods, utilities, smart cities, smart chain, healthcare, manufacturing, agriculture, education, construction, and several other areas. Now, we argue that with this number of devices comes different challenges that has to do with memory, challenges that has to do with energy efficiency, challenges that has to do with interoperability, because we're talking about devices with different capabilities, both homogeneous and heterogeneous devices, and devices that uses different communication strategy. So for the purpose of this research, we are only going to focus on routing. That's the nature of communication between these devices. And we try to propose an adaptive routing protocol that will be able to handle at least 3, that will provide at least 3 different solutions that has to do with energy, solutions that has to do with mobility, that's devices that are moving up and down within the applications, and then also solution that has to do, we realize that there are devices that have their own energy source. So either mains powered or solar powered, and these devices would not require routing, energy saving routing. The routing protocol that we propose in this category is the RPL routing protocol, which stands for IPv6 routing protocol for low power and lossy networks. RPL has, it comes as a default routing protocol on over 10 to 12 IoT operating systems, from Contd operating system to Riot OS to Lind OS and several other IoT operating systems. Now, RPL is a distance vector proactive routing protocol, which utilizes the directed acyclic graph concept of routing. Now, it is defined by a series of standards and specifications, which defines the mode of operation of the routing protocol. Now, each of the routing metrics that are used to choose path and preferred parent within the objective function or within the routing protocol uses a set of metrics which are also defined in the RFCs. RFC stands for request for comments, which specifies, which gives the standards and procedures and specifications in order to use the metrics. Now, those metrics are classified into two. We have the node-related metrics and then the link-related metrics. Within the node-related metrics, there are three metrics. We have the node state attribute, we have the hop count, and then the node energy. Likewise, within the link-related metrics, we have four metrics within that category. We have the throughput, the latency, the ETX, and then the link quality. At the same time, RPL uses a trickle timer algorithm, which specifies how control packets and packets within the network, how they communicate, how nodes joining the network communicate by exchanging requests to join networks. Similarly, there are also network requirements which are defined by the RPL, which specifies the nature of implementation environment, whether in an urban setting, whether in industries, whether in a home, whether it's a home IoT network or a building. These are all defined by a set of standards and specifications which are defined within the RPL objective function. RPL has two default, it comes with two default routing protocols. The first routing protocol is the objective function 0, which uses hop count as a means for selecting path and preferred parent within the network. Now, hop count is a node-related metric. We argue that this objective function, the first routing protocol in the category does objective function 0, only utilizes hop count, which is a node metric, thereby ignoring all the other link-related metrics. So this only uses the traditional shortest path routing algorithm, which just counts the number of hops from source to destination. Similarly, the second routing protocol, default routing protocol, is the minimum rank with hysteresis objective function, which uses the expected transmission count. This ETX is also a link metric. We argue that it ignores all the other node-related metrics in the network. They were only considering the link. So we came up with an enhanced energy saving objective function, which uses a combination of three routing metrics, one for node and then two for link. Therefore, we try to ensure that we select an optimal route at every computation, such that the remaining energy of the nodes will be put into consideration. Likewise, the link quality, and then the expected transmission count of the node. And as I have said earlier, we are trying to develop an adaptive routing protocol that can handle both energy saving, mobility support, and then energy scavenging nodes. That's nodes that have other source of energy, but for the purpose of this conference, we're only limited to enhance energy saving. This is the design concept of the adaptive routing protocol. We define a set of priorities for choosing each objective function within the routing protocol. We said for energy saving, it's going to consider three metrics: remaining energy, ETX, and link quality. But then for it to select energy saving as a priority, it has to follow a particular set of considerations. The first consideration is that the energy within energy of a node must be less than 50%. That's the first consideration. Then secondly, we said that the network must have a very high packet transmission rate. Then thirdly, if there's no available route, but the route with the least energy, also energy saving is going to be selected as the routing protocol. Then fourthly, we said if the intention of routing, if from this word go, we want to just utilize the energy saving routing protocol, we can just go ahead and invoke the energy saving routing algorithm. And then if also the last point is if the operation is going to go on for a length of time, and then we need to save energy within our network, then we're going to choose the energy saving routing protocol. Within the energy saving, there's a process or algorithm that we designed. First of all, once the energy objective function has been initialized, objective function is only a way by which the RPL chooses the metrics of routing. It receives the metric values and then the metrics within the network in order to make its selection process. Thereafter, it tests whether the previously collected packet is previously collected route is the same or higher or more economical than the previous route, and then it selects the best route at every turn of the computation. We want to implement our protocol in 3 phases. The first phase is actually to conduct a simulation and then see how the behavior of our routing protocol within a simulation environment. And then secondly, we intend to develop mathematical models to validate those simulation results. And then lastly, we tend to implement the routing protocol in a real device in order to see some of the performances. We know that some environmental factors might play a role in trying to limit the performance of the routing protocol. So some of the simulation parameters that we used, we said that RPL has implementation in quite a number of IoT operating systems, one of which is Contd OS, version 3.0, we utilized for our simulation. We also utilize a 200 square meter simulation environment with different node distributions and node varieties from 10, 20, and 30 nodes. We also used emulated nodes, Z1 modes. We set our simulation transmission range to 50 meters, and we conducted the simulation for 30 minutes. Now we try to be unbiased in our setting so that we get the maximum performance of our routing protocol by ensuring that we deploy our nodes randomly within the environment. And also we utilize the unit disk graph medium, UDGM, which allows us to see what is happening at the background at every computation. A point I forgot to mention was that RPL is initially designed for static nodes. That means nodes that are not moving, nodes that are not mobile. So in order to simulate mobility within the objective function, we had to download Bone Motion, and then we use it as a plugin within our operating system in order to provide us with different mobility models and to implement mobility within our objective function. Then some of the mobility models that were utilized were a random waypoint and random walk. And we did this because there were several researches that try to ensure that random waypoint and random walk are the actual models that represent node movement in real time. So we try to build on that. Our simulation setup, we said we used a UDGM environment. UDGM allows us to see what is happening at the background, which node communicates with which, and then it also shows the range of transmission and then the interference range. The green circled area is the transmission range, while the gray area is the interference range. That means node within the green area can communicate directly to the sink, but nodes at the within the gray area have to communicate through nodes that are within the green area, which is one hop neighbor to the sink node. Also, we designed our simulation output window in such a way that it displays the performance, the exact performance in real time of different nodes in the network. Each time a packet is received, we ensure that it transmits its link quality the consumption energy it uses within the communication, as well as the remaining energy. Now, we try to reflect the exact remaining energy of nodes down to the least figure. That's why we had to introduce a different empty 16-bit integer within the Kuja quantity in order to compensate for that. And also, whenever a packet is received by the sync node, it transmits all the several informations. It transmits the delay, the latency it took. It transmits the number of hops. And we also left a lot of fields undefined that we intend to use in our future research. Now, while attending several other talks within this conference, I realized that most of the talks are within security related. And that gave me some ideas on how to incorporate security within my my research. Some of these fields are going to be used for security. I've already had the idea down and I've written it down. It's going to be used in my future research. Some of the simulation results that we've gotten, the most of the performance evaluations, packet delivery, energy consumption, and delay. These are the most common performance metrics to be evaluated in a routing protocol. So we implemented our objective function using 10 nodes, 20 nodes, and 30 nodes. We deliberately used a minimum number of nodes so as to know the exact performance of our routing protocol before we deploy them in high density network. We've also utilized them both in random waypoint and random mobility model. And we realized that the more the number of nodes increases, the lesser the packet delivery, unlike the energy, which is a complete opposite of the PDR, where the higher the number of nodes, the higher the energy consumption in the network. Now, we did this as an average. We collected it as an average because it's difficult to, and it's time consuming to collect individual nodes performances within a network. So we had to do it in form of an average. We introduced a metric, which is the parent change, because we realized that each time, like we said earlier, each time a packet is received, it has to undergo several tests in order to determine which is the best part or which is the best preferred parent within a network. And we've recorded a certain number of exchanges within our objective function. Also, we model for end-to-end delay in milliseconds, which each time a node without mobility performs in a non-mobile network performs better than when mobility is implemented within a network. Now, the second aspect of the talks is the numerical analysis, which is the mathematical model for our validation of simulation results. Now, we had several options to use different probability distribution models. So finally, we settled with Bernoulli probability distribution, which allows us to define certain values, which we call psi values. Now, these psi values are exact, they represent the probability of success for simulation. We've conducted more than 45 different simulations with different node setting, node design, mobility implementation, and different routing protocols. So we had to go back to our simulation and then use this probability model in order to determine the probability of success of each of those 45 simulations, where we recorded a certain number of certain values, which are known as psi values. This formed the backbone of our mathematical model. So the first one we tested within our category was the PDR, and we said is a received packet over sent packet times 100. Now, each time we have a received packet, we said we had to multiply by the probability, which is our psi values, in order to determine the exact PDR of the network. Then second metric that we considered was the end-to-end delay, where we used the Markov chain for Q delay of MM1 systems. And this is a very long computation. So we just had to cut it short and then bring the final model that we've developed. We use the end-to-end delay to determine the propagation delay, processing delay, queuing delay, transmission delay, number of packets in the system, delay, queue delay within the system. So we finally arrived at the complete end-to-end delay system, and we said it's a summation of all values, 1 plus alpha, which is the system utilization, and then mu is package departure rate minus packet arrival rate, time is our psi value, and then time is the hop count, and number of nodes, n is the number of nodes, and t is the total duration of time for the simulation. Our energy consumption model followed the basic, most common energy models in IoT. And also we came up with our final model where we had to involve our psi values multiplied by energy model. And then we tried to show, we realized that each time a node starts within a simulation, there is a certain amount of energy that goes to the node, which is known as peripheral devices. There's a certain amount of energy, so we had to model that and put it in our final mathematical model for energy consumption within the network. So finally, we received, we collected simulation, both simulation and computer results. We tried to compare them, and there's not much difference. It's still within the acceptable range. So it's assumed that we've finished our simulation, and we've also conducted a mathematical model, which has validated the simulation results. So we are now at the last part, which is trying to implement this routing protocol on real system, real devices, real IoT devices to record the performance, which is going to be done very soon. So in summary, we've proposed an energy objective function that combines 3 routing metrics, which contain both node and link metrics. Now, our objective function has showed superior performance when compared with the standardized versions of the RPL objective functions. And we also produce a mathematical model, which we use to verify our results within the simulation. So thank you very much for listening.
Thank you, Abubakar. That's a very fascinating talk. I loved it. And you've got a number of questions there. Really interesting, because with IoT, part of the problem is they have low memory, low compute. Therefore, from a cyber standpoint, it's easy to conduct various type of compromises against them, especially compute utilization exhaustion. So you can exhaust their battery power or their CPU, and you can launch a denial of service attack to them. Yeah. So the questions are, you're going to have to do this in a real life network to benchmark your work against the results from simulation and the results from real life network to see how they compare in real life.
Yes.
But before you do that, did you use any other simulation model or environments rather than just the UDGM? Did you look at other simulation environments, i.e. like the network simulation, NS3, NS2, or Simulink, or various other, or even MATLAB? Did you investigate other simulation environments?
The interesting thing about some of these IoT is that they have their own operating systems. So one performance in a particular operating system is the same performance in other operating systems. The only difference is the capacity of most of these devices. It's maybe it's a capacity for RAM, it's capacity for memory. These are the only things that might try to play a role in the performance of these devices. But the operating system I use, the UDGM, is included within the Kuja simulator, and the Kuja simulator is included within Contd operating system. So the operating system I use is a Contd operating system, which is already an operating system for the Internet of Things. It uses Linux commands and several other Linux implementations for that performance. So I believe it's still the same, even if I use Riot OS or Tiny OS or any other IoT operating system. The performance will still be the same as far as simulation is concerned.
So the real crux will be trying it in real life network and see how the performance benchmark the two.
Yes, okay. Because we thought of challenges that has to do with all these environmental challenges that naturally affects the network. in terms of range, communication, and others.
We've got time for one more question before we close the call. So the question here is that because your objective is about adaptive nature, adaptive routing, you considered 3 feature sets, 1 feature set on the node and 2 feature sets on the link.
Yes.
What was the rationale? And did you try all that combination before you settled down for 1 node feature set and 2 link feature sets?
Yes, I think I forgot to mention that I'm a 4th-year PhD student where my Viva is just around the corner. So I think I spent, in my 2nd year, I spent almost 2 years trying to reconcile between this very thing that he's saying. I tried different combinations. I had to wait for the exact one that worked. So I tried using 2 links and 1 node. I tried using 2 nodes and 1 link. I tried different combinations because I used a mathematical model known as permutation and combination. It's something that I use. So I tried different combinations to see which actually worked better at which setting. So it took a lot of time to get to this conclusion, and finally I finally got what actually worked.
So that's the optimal setting for you.
Yes, that's the optimal setting for my routing protocol. Yes.
Okay, that's the much we can take because of time. Thank you very much. And ladies and gentlemen, before you go, there's a keynote starting at 1 p.m., just an hour from now, by Dr. Phil Legg, Associate Professor in Cybersecurity from West of England University. So I would like you guys to please try and convene again at 1 p.m. UK time. That's an hour from now. With that, thank you, everyone. And thank you, Abubakar, and good luck with your Viva.
Thank you. Thank you.
Speak soon.